Morning, thank you. Yes, this is from a British science fiction author, Charles Stross or Charlie Stross, and what he's talking about here is where they're like these sort of little ants that sort of work on these treadmills in these giant companies, executing the processes, the heuristics, the algorithms of those companies very, very slowly. He refers to that as artificial general intelligence, but at the corporate scale. So corporates becoming AGIs, essentially. So I thought it was quite a fun place to start, because I'll be talking about some stuff that's been on my mind for a little while. If my clicker works, which it did a minute ago, which is about how the world of work works, actually. In particular, how flow works. So how work flows through organizations, flows through value streams, the sort of domain model of that. But because it's me and because I've been thinking about a bunch of other stuff over the last since about 2017, to do with things like agent-based models, we have to call this agentic now, don't we? If we're cool. I'm not cool. Agent-based models, different forms of AI. AI is very overused, but agent-based models are a form of one of the original three forms of AI. So I've been playing around with those since about 2017, trying to understand whether you could build something that demonstrated how the world of work works, how flow works, like a simulator, a bit like SimCity for companies, if you like. So we'll come to that in the end. We'll come to that, the domain model of the world of work, but I'll talk about some other interesting stuff, hopefully, in the middle. But I'm going to start with this question, which I'd like you to ponder over the next 40 or so minutes. If you were in charge of building Lego sets better, what single change would you make? If you worked for Lego and you were in charge of building Lego sets more fun, better, what single change would you make? So I won't dwell on who I am. I work for a company called ThoughtWorks. We're a consultancy. We're about 11,000 or so people now. When I joined, we were about 600. I've been there nearly 20 years, but as our former CIO said, I don't know why everyone says I've been here 20 years, because tenure is not capability. It's just longevity, right? But I have been at ThoughtWorks nearly 20 years. I've done some stuff. I wrote this with Martin Fowler about microservices back in 2014. I'm also doing a talk on 10 or so years of microservices. At the moment, you can find that online, and I'm currently writing this with two of my colleagues, Patterns of Legacy Displacement. It's in fits and starts, and you might think, why would you bother writing something about patterns of legacy displacement? And the answer I normally give is because someone has to. And it turns out it's us, which is frustrating. But anyway, there you go. We're doing it so no one else has to. That's me. So I want to start off with this statement that work flows as information through value streams. We all probably know this. We all probably have internalized this, given the audience at this conference. It's also a subtitle, Why Shared Test Environments Should Be Nuked from Orbit. So there's quite a lot of information in this subtitle. So work, what do I mean by work? What do I mean by flow? Information and value streams. So in terms of work, I mean any sort of thing that we're doing as knowledge workers, right? So whether we're creating ideas, whether we're writing user stories, writing tests, writing code, all of that is work that we're doing of different types. The interesting thing there is it's all sort of invisible work until it's sort of code, right? And interestingly, when you have work flowing through a value stream, work starts off, the stuff at the start of the value stream starts off in its least valuable state, and it ends up at the other end of the value stream, say in production when it's deployed, in its most valuable state. In the same way that if you build a car and you have a value stream of supply chain and then a value stream building a car, it starts off with lots of much less valuable bits, which is the parts of the car, and it ends up with the thing that people want to buy, which is the actual car, the valuable thing. And the bits in the middle, not so valuable. This is why we talk about not holding on to inventory, because inventory is cost. Right, stuff that's in the middle that isn't the finished product, that is just cost. And it's the same with what we do. Partially completed ideas, partially finished work as part of our software value streams is inventory, stories sitting around in Jira backlogs for years and years. Okay, hands up. I can't actually see many people in the room. Hands up if you've got something on a Jira backlog that's over 2 years old. Yeah, 90% of the room, if not more. Inventory sitting around. If that was in a factory, right, and you just had 2-year-old bits sitting in front of machines, do you think the managers of the factory, the people managing ERP and so on, would be happy with just piles of stuff sitting around with nothing happening? Maybe they're faulty, maybe we don't know what to do with them. This used to be useful, not anymore. No, we wouldn't be happy with that, would we? It's weird that we sort of don't apply the same sort of principles to what we do in knowledge work. We have this invisible inventory. This is what Don Reinertsen talks about in the brilliant book, which I'll come on to, Principles of Product Development Flow. One of the big problems that we have with what we do is the work is invisible. And so making it visible, as we've heard quite a lot, actually we definitely heard in the World of Warcraft talk yesterday, making stuff visible, super important. So work flows as information through value streams. What do we mean by a value stream? I'm sure we've all come across value streams. I'm going to do a brief, sort of recap on value streams. This is a very simple version of a value stream map from a real client from several years ago now. And what this shows is a number of things. You have a number of value-adding activities. Each of the value-adding activities has a cycle time. In this case, you've got development, which takes 3 days. You've got 1.5 days of testing and a half day of deployment. We're ignoring the stuff that happens before we hit the team's backlog here, right? So again, I think this is referred to by Don as the fuzzy front end, or the business requirements documents and business people kind of arguing about priorities and all that stuff. So work hits the team, sits there on average 2 days, takes 3 days to finish a user story from a development perspective, 1.5 days to test, and a half a day to deploy. But what you might notice here, of course, is the 2, 10, and 30 on this. So these are the wait times on the value stream. These are the length of time inventory is sitting around unfinished, not earning us money, right? Just sitting in a queue somewhere, waiting for the next value-adding activity to happen, waiting to be turned into something more valuable. So we've got 10 days between development and testing. That's on average. That's like a 20-day period sitting around, 4 weeks or so, right? 4 weeks of business days. We've got 30 days before it's deployed, before the code is deployed, after it's been tested. On average, that's like a 2-month release train, if you think about it that way, on average. So if I put some terms in as well. By the way, everyone sort of says cycle time is this whole thing. It's not. Cycle time in Lean is the cycle time for each activity, right? And interestingly, it's not the whole thing. Lead time is the whole thing, depending on definitions. So you've got wait times, you've got value creating or cycle times, and you have production lead time, which is the whole thing. And in this case, we've got a total wait time of 42 days, value-adding time of 5 days, so the production lead time to get something done is 47 days on average before we see the value of the stuff we're working on. It's no wonder our colleagues get frustrated, right? They're like, but you've done the work. Like, where is it? Where's the money? Show me the cash, right? I was thinking about, there was a TV show in the UK called Bullseye a long time ago. And it was like a darts. We play a lot of darts in the UK. And it was a darts like game show where you'd have a professional and you'd have like someone, someone else playing darts, and they'd kind of try and win a prize by throwing darts at a dartboard. And at the end of it, most of the time they didn't win. And so the game show host would say, "Oh, it's a shame you didn't win. Let's show you what you would have won, what you could have won if you had won." And a curtain would come back and there'd be a car or a boat or like a caravan or something, or a big TV. Let me show you what you could have won. I always think about this kind of, these kind of states, these value streams as a bit like that. You could have been earning money, right, for 42 more days, but you haven't been, because it's just been sitting in a release train, waiting for your safe release train to safely safe along. Of course, value streams don't normally look as simple as that. This is another real one from another real company I worked at. So this is a more sort of realistic one for a large organization that's accrued lots of processes over time. I'll talk through some of the iconography in a moment. But fundamentally, you've got the fuzzy front end up here. So this is all like business requirements documents being specified and gathered and written, enterprise architects doing their enterprise architecture stuff, solution designers designing solutions, coming up with options, choosing options, putting it into review boards so the options can be approved or not. Architecture says no board, and architecture review board says no. Then you've got stuff in the middle, which is data, people doing data things. And then you've got a little bit over here. There's one post-it in there, which I'll show you in a minute. One post-it that's writing code. All this, and then all of that is testing. Familiar? A lot of organizations, especially bigger organizations, look quite a lot like this. And the reason is, over time, these, what might start as something quite simple, like this, ends up accruing more process, accruing more checks, accruing more risk-reducing steps. So we'll have not just one testing phase, but we'll have systems integration testing, user acceptance testing. We'll have regression testing, each independently. And you know why? It's because on Black Friday, once someone changed a GIF and they brought the site down, right? So now we have 12 weeks of regression testing. And that's a reasonable thing to do. You add more process. We add more process, make it less risky by adding more stuff. We kept working on things that we didn't really, that were fuzzily specified. We kept getting stuff wrong when we were in development. Well, we just think more. We'll have more people thinking about it up front, right? Sounds entirely reasonable. Who creates these in work? Who actually spends time looking at the value streams? We've got a few hands going up, that's good. Often I get asked, as a result of doing this talk, what single piece of advice would you give? And I often sort of say, well, as a consultant, I turn up with a bunch of tools. That's my job. I've got a big bag, 2 big bags, maybe even more big bags of tools. And when I turn up, I know how to use these tools. And the other thing is when I turn up, I've got time to use the tools. Often the organizations I'm working with, the people I'm working with, they haven't got any time to actually look around and look at their world of work, look at the system that they're working within. So that's the advice I'd sort of give you, if I could, is take a step back if you can and look at the system of work that you're working within. Use things like value stream maps to understand it. And interesting things can happen. In this case, we showed this to the equivalent of the CIO. There's not that much detail on this. It's like, there's some numbers of days in some bits. We just showed him the whole thing. And he said, how the hell did we get into this state? And he went crazy. And they made lots of changes, so that's good. But just by looking at the overall value stream. Now, I promised you to look at some of this iconography. So you've got 3 types of wait time represented on that value stream. The first is coordination. So this is when one team or one person is waiting on one or more other teams before they can get their stuff done, right? So it might be you're waiting on, I don't know, in our case we've got a couple of things here which I'll show you. In this case, the developers in this box, and there's one of those blue post-its is a developer writing code. They're waiting on 2 sets of data architects, each updating their canonical data models. I don't think they got the word canonical. But yeah, you've got one type of data architect, another type of data architect. They're both iterating on their canonical data model until eventually they're happy. Yes, our global data models are synced, they're in agreement. Out pops something for the developers to work on. So these folks can't get started on anything until these finish their works. That's synchronization. We then have scheduling. And scheduling appears in lots of different places. Meetings, that's kind of scheduling. Cadence, anytime you have something that happens on a regular cadence, is kind of scheduling. Architecture review boards, that's a classic example of something that happens on a schedule. Maybe you meet every month to say no to things. In this case, it was 2 to 4 weeks, so on average, so 4 to 8 weeks. But you have lots of these sort of cadence, these things that happen at a regular cadence. And the interesting thing about this is pernicious. It sounds like a good idea. We'll have these valuable people. Well, they've got valuable things to be doing with their time, so they'll only meet once every 4 weeks to make these decisions on the architecture review board. Of course, what happens is that as a result of that, loads of work gets queued up waiting for those decisions to be made. You're essentially putting a complete blocker on work flowing through these value streams. And in fact, in the book Accelerate, which is the summary of a lot of the previous State of DevOps reports, you probably all know this, change request boards, architecture review boards predict low organizational performance. And I'm using that word precisely, predict, in the statistical sense. If you have one, it predicts you're going to be in the low-performing group of organizations in terms of revenue or whatever. Architecture review boards. You can, of course, if you have an architecture review board, improve some things. You could meet more regularly, right? Just by meeting more regularly. If you meet every 2 weeks, not every 4 weeks, guess what? You double throughput. That's pretty cool, isn't it? Maths. You also have these other wait times in here, queues, and queues are everywhere in our world of work. They're incredibly pernicious, and we can't get around them, and that's fine, because queues exist everywhere in real life as well, and I'll show you some examples in a minute. But queues are another form of wait time. And of course, the length of time a piece of an item of work is going to wait in a queue depends on the depth of the queue, and how often you reprioritize, reshuffle, or in the case of the 4-year item on the Jira backlog, just keep pushing it to the bottom, because actually no one ever wanted it in the first place. This is why Daniel Terhorst-North, I believe, he's got a lovely thing he does when he turns up to do his sort of coaching. He says, right, first of all, just delete your entire backlog, all of it, or at least anything over a certain amount. So queues, work sitting in queues. And this is where, again, it's this invisible inventory that's sitting around not earning us money when it could. You know, every day, something that could have been in production, right, could have been earning us, say, 10 bananas a day, but is sitting in a queue, is 10 bananas we've lost. Right? It's the opportunity cost of wait time, the opportunity cost of things sitting in, not even just opportunity cost, real cost, right? We're not making that money. And queues, as I say, are everywhere. So in this case, we've got the business folk want a bunch of changes done, so they're all sitting in a queue right at the top of the fuzzy front end, right at the front, the fuzzy front end. You've got a bunch of solutions waiting for solution architects to come up with options, sitting in a solution options queue. And then you've got a bunch of work that's been specified to within an inch of its life and is waiting for the integration team to pick up. 3 types of wait times, and sometimes we have all 3 of these at once. And if you're paying attention, you might have seen the signpost where we have all 3 of these at once. And it's why we still have this on hold on the ThoughtWorks technology radar after about 15 years or something. And that's shared test environments. And this is why this should be nuked from orbit, because every single type of wait time applies to shared test environments. Right? You have to wait for other teams often to finish work. I'm waiting on this team to finish that so they can upgrade the version so I can put that. I often have to wait on a schedule. Your turn is in 6 months' time or in 6 weeks' time, so you can't do the integration until then because this other team is doing it until that point. And often there's a synchronization. Also, synchronization. Often there's a queue that you're sitting in as well, waiting to get there. So there's 3 types of wait time associated with these. Nuke them from orbit. The funny thing is about these, the reason I often get, when I ask, I'm like, curious, you've still got one of those? Oh. Yeah, well, we've got this thing, it's expensive, we can only have 1 of them. We've got this big SAP thing, it's really, we can't have more than 2 of those. You've got a production one, we've got one for integration testing. All right, okay. But how much does it cost? Oh, I don't know, £50,000. Oh. Like, how quickly are you going to rack up 50 grand's worth of costs of stuff sitting, waiting to get into that test environment for want of spending that money on a new thing, a new copy of SAP. It's a funny thing about economics. Until you make these things visible, the economics aren't clear. But as soon as you start making these things visible and start associating money with things sitting around not making it, all sorts of other decisions become more obvious to make. So shared test environments, nuke them from orbit. Life moves pretty fast. If you don't stop and look around once in a while, you could miss it. So why is AWS a thing? This is related to queues as well, and queuing theory. So this is my attempt at an XKCD joke. You can do these online, they're generators for these things. So imagine the CIO, he's reading Computer Weekly, paper format, picked it up and, oh, I need a platform. Apparently it comes with a DevOps, and the developer says, yeah, sure, why not? The reason AWS is a thing is because platforms as a service, specifically actually in infrastructure as a service platforms, are MMC queues where C tends to infinity. Now everyone's completely au fait with queuing theory, right? No? Okay. Maybe I'll unpack some of that later. So I'll do it now. Quick recap on queuing theory. So this is very clear syntax, what I'm sort of describing, the semantics of queuing theory. This is why we're building platforms all wrong. So if you think about queuing theory, you have a queue of stuff, right? So it could be Jira items, backlog items. It could be people queuing to get some food for lunch. I'll come back to that. It could be people waiting in the line at a supermarket. You're waiting to check in at a desk. It could be, as I say, Jira items in a backlog. You essentially have a queue of things that need to be processed. You have producers pushing stuff into the queue, and you have arrivals into the queue, and then you have a number of things processing items on that queue. If it's a supermarket, the number of people who are able to process the food that's going through the till. If it's same for an airline service desk. So you have a service node. Then you have departures from the queue. The rate of departures is dependent on how quickly the service nodes are able to process those departures, and obviously depends on the number of arrivals and the distribution of arrivals. And you have different types of queue depending on these three things. So in one hand, you've got an MM1 queue where you have a single service node that's taking items off a queue. So this is a supermarket check-in, a checkout, right? So you've got one person processing items, or an airline service ticketing desk. MM1 queue. You then have an MMC queue, where C is the number of service nodes, right? So you could have two to the n, you could have C service nodes. And this is how you describe these different types of queues: MM1, MMC, or MM2, MM3, etc. So the reason AWS is a thing is because they invert this relationship between the time it takes to process stuff on the queue and the number of service nodes you need to process it. So if you think about a traditional operations team, right, in a traditional operations team, you've got a bunch of people who want databases, and they fill out a ticket for a database, and then you've got a queue of tickets for databases, and then you've got really smart, highly trained, skilled people making databases for them. But the number of databases they can make, or create, or provision is depending on the number of people that there are, right? So the only way to scale traditional ops teams is by adding more highly skilled, expensive people, right? Traditional ops teams. You've then got what we call in ThoughtWorks the half-assed private cloud, or half-assed private cloud infrastructure as a service team. This is where you put an API on the front of a traditional ops team. Maybe it's got a nice user interface now, so you don't use ServiceNow anymore. You have a pointy-clicky thing, I'll have this, and I'll have this, and I'll have this. But it still goes into a queue for the expensive people to actually provision for you. And you can tell if you've got one of these, because you'll get a company-wide announcement that says, hey, we've got a new infrastructure as a service platform, new private cloud, and it takes the same time to get anything before and after. That's the signal for one of these. You've then got something we've started to see, you've then got the reason that AWS is a thing, because AWS inverts, or certainly things like EC2 or the ability to provision infrastructure yourself, inverts this problem, right? So we're no longer reliant on hiring lots of smart, expensive people, right? We decouple the rate at which we can provision stuff, infrastructure, from the number of people we've got in the ops team. We can provision stuff only at the rate that the hypervisor can service the request, right? So C, where C tends to infinity. And then you've got the next thing, which is the half-assed platform engineering team, which is the newest iteration of one of these things, where you get really cool self-service infrastructure, which can provision stuff really, really quickly. And then you put a platform team in front of it, And you still have to scale the platform team to service the requests coming in from everyone for platform features. So that's that. Now, this is why AWS is a thing, because some of these stuff are slow and expensive, and some of this stuff isn't. And the one that isn't is AWS, Infrastructure as a Service. And I'm going to flash that just to drive that point home. Like that. Woo! Yeah. If you want to read a bit more about the half-assed or superficial private cloud, you can read my colleague, or former colleague, Evan Botcher's writing about that on martinfowler.com. But it's essentially where you're just putting an API over your traditional ops team and pretending you've got a platform. So this is the second part of this cartoon. Okay, boss, we've implemented a DevOps. We have a platform too, but we still can't get anything done. And this is a very common thing I see. So I promised a bit more of an exploration on queues, on the world of work and that kind of stuff, and that's what this next little bit is about. But first I need to tell you a bit about something called generative science, complexity science. Well, not complexity science, but generative science. So generative science is about simulating the real world, making simulations of the real world, and then playing with the simulations and seeing if those simulations can tell us anything about the real world. Some examples of that. This is in NetLogo. Everyone remembers logo? Anyone written any logo in the past? Turtles, yeah. This is often used to teach children how to write code, right? So you get a little turtle, you can move around, you like go left, go right, etc. This is NetLogo, multi-turtle. This is a multi-turtle logo or multi-agent platform. And in this is an example of birds flocking. So you set a set of initial parameters, how close the birds can get to one another, their turning radiuses, how far they can see in front of them and so on, and their speed. Very simple parameters. And then you run the simulation, you see what happens. And in this case, you get chaos, right? That's nothing, it's like Brownian motion, chaotic motion, Brownian motion. But if you tune those parameters ever so slightly, something interesting happens. This undergoes a phase change, and you get something quite beautiful emerging in the simulation, in the model. You get this flocking behavior starting to emerge. Right. And this is what generative science is about. It's about saying, can we come up with a set of simple, maybe even simplistic in some senses, models that describe the real world enough that we can play with them and understand a bit more about the real world. It's a bit less of a toy example. So this is another agent-based model showing the spread of viruses, right? So in the population. And again, you can fiddle with some parameters, the rate at which the virus affects people, the distance people can get to one another, and so on. And you can sort of simulate how viruses spread. A lot of the modeling for the pandemic was done using these at very large scale. So not using NetLogo, didn't use NetLogo. But that's where the 2 meter thing in the UK came from, right? That's what, is it 1 meter, is it 2 meters? Is wearing a mask, does that help, does it not help? All that stuff, they simulated using these models. And in fact, ThoughtWorks, I used to have a slide on this, but we helped a university in Mumbai, the University of Mumbai, build an agent-based model that simulated the entire population of that state. It's hundreds of millions of people. Very cool stuff. So you can use these for real-world things, right? You can understand how the world really works using generative science and agent-based models. Back to following the work. Or why traveling slower often makes you go faster. So we've got these 3 types of wait time. The thing is, we can start to do things like model some of these in software. We can create these agent-based models, generative science-type models, to demonstrate some of these principles, or why these sort of wait times and things are so pernicious. The first thing, the principle of congestion collapse. When loading becomes too high, we will see a sudden and catastrophic drop in output, or why it's important to have slack on your team, right? Why it's important never to be working at 100% capacity. Because systems that are prone to congestion collapse, and the teams that we work on are a system prone to congestion collapse, they undergo this sort of catastrophic phase change, if you like, when they become overloaded, when they reach 100% or tend towards the maximum capacity of the team. And we've probably all seen this, right? Everyone's working flat out. There's no slack at all in our teams. And then suddenly there's like a priority shift or something, and we need to like reprioritize some work. and then suddenly everything just collapses, and nothing gets done. We need to reprioritize, we need to stop doing this and start doing that. Everyone's just doing lots of stuff. That's a kind of catastrophic congestion collapse on our teams. There's another example of this, a simple example of this, which is cars on a motorway or an interstate or highway, whatever, on the Autobahn. So this is a very simple model of cars traveling on a highway. What you can see here is this catastrophic congestion collapse, right? They start bunching. There's no accidents, there's no incidents causing this. It's purely a function of the number of cars, or the number of agents in the simulation, number of cars on the motorway, and the speed at which those cars are going. So when we're driving along and all those red lights go on and we have to you back up in heavy traffic, there's no often no incidents, there's no crashes or anything. It's just a function of the number of cars and the speed at which they go. And in highways, designing highways, there's lots of interesting things you can do, right? So in the UK, we have smart motorways now. So we will downgrade the speed limit depending on how busy the road is. Because if you lower the speed limit, you increase the amount of cars you can have without going into a collapsing state. So this is an example of the peak throughput principle. You can control occupancy to sustain high throughput in systems prone to congestion. Here's an example. All I've done here is reduce the number of cars. And there's another example I could show you, which is reducing the speed. And they settle into this flow state. There's no collapse anymore, right? They don't undergo the phase transition. And we can do that on our teams, right? So when we're on a system prone to congestion collapse, we can control occupancy to reduce the probability of that happening. Create slack, like use work in progress limits, for example, right? Limit the number of types of work that we're doing for a particular service type at once. These are all mechanisms from Lean, from Kanban, to improve the ability to resist congestion collapse. Here's another principle. We're in queue size. The second queue size control principle, don't control cycle time, control queue size. Now, we've become obsessed with DORA and the 4 key metrics. Fantastic that they are. But cycle time, as they refer to, commits to production, right, as opposed to lead time, whatever else we can call it, is a trailing metric, fundamentally. Right? If the moment we start seeing cycle time go up, right, we know we've got a problem, but it's after the fact that the problem occurs. We don't know why cycle time is blown out. We just know that it is. It's a trailing metric for something going wrong. And that's cool, but there is a leading metric that you can use in advance of cycle time to understand before cycle time blows out that it's going to. And that's queue depth, the number of stuff waiting to be processed. As queues grow, cycle time increases. It's Little's law. Oh, that's not Little's law, actually. I'm wrong about that. So here's a question. Yesterday, how long did you have to wait for lunch? It's actually pretty good, wasn't it, here? Who's been to a conference or an event or a buffet, maybe a wedding or something, where the queue goes on forever? Yes, everyone has, right? You're just sitting there waiting. God. This is a function of queues growing, obviously, and having it's an MM1 queue, when you have like one buffet table. Actually, interestingly, it's an MM2. There's actually 2 queues in this case. We've got 3 queues. There are 3 queues, are there? There's one up there as well. Oh, shh. There's one up here. Blimey, 3 queues. 3 different systems. But many places, you just have a single table and you just queue, etc. And this is what this looks like, right? So you've got lunch being served at 1 o'clock, and then you've got the people who are in the, who are exhibiting. They're sort of arriving at the lunch tables, and they're fine. This is what they're doing over here, and they're getting their food, and then they're not having to wait a long time at all. And then the sessions finish, and a ton of people, the thundering herd of hungry people, turn up at 1:10, and then at some point later, those hungry people leave. So this is basically time, and this is the number of people in the queue. So lunch is served here, and this is the rate of departures from the queue. So you've got arrivals, departures, so sessions finish. If you're waiting for cycle time to tell you you've got a problem, you're going to wait until 1:35 before you know that you've got a big problem with your lunch being served. Whereas if you measure queue depth, you will know a minute after the queue forms. This is why supermarkets, this is why airlines have cameras, like looking at the number of people waiting for check-in. Because you get the ding-dong, everyone trained for the tills, please go to the tills. It wasn't that surprising, but I'll take it. Yeah, ding-dong, everyone goes to the tills. Because if you look at the queue depth, if you look at the number of people waiting, it's a leading indicator of things about to go wrong, which we can, of course, do with our teams as well. You don't have to wait for cycle time. You can look at the amount of work building up beforehand, waiting to be processed, and that will give you some time. Okay, batch size queuing principle, reducing batch size reduces cycle time. We've sort of come across this, I'm sure, before. So I'm going to go slightly over the time because I've got 6 minutes on my clock. We started late. Is that all right? Or 5 minutes late. 5 minutes. 4 minutes. You're going to lose 4, 3, 6, 7, 10 minutes of your break. Batch size, queue depth, and cycle time, this is the relationship between them. What we have here is 2 big batches of work, each being delivered into production after a period of time. 50% there, 50% there. So it's 100% of the requirements, 50%, 50%. And this is what you do, this is what you get when you take exactly the same amount of work, but split it up into smaller batches. All right. The first batch is delivered much, much more quickly and starts earning money. The next batch is delivered much, much more quickly, starts earning money. So by the time the final batch of work is being delivered up here, this is Little's law, the final batch of work that's been delivered up here, all of the stuff before it has been earning money that entire time. And that cumulative effect, the cumulative increase in value, compounds over time. And I'll show you a little bit about that in a sec. Don Reinertsen says, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. So, there's a photo there if you want it. No. Read the book, it's brilliant. That's what you should do. So how flow works, a curious domain model of how we work. So can we simulate the world of work? Can we simulate some of these economic effects? Can we simulate using things like agent-based models, generative science? Can we understand using things like complexity science, generative AI, generative science, and queuing theory, how the world of work works, and come up with some interesting results? I think we can. We've started to do this. I've started to sort of build a tool that will take something like this, a value stream map, and allow us to run simulations based on these value stream maps, based on agent-based models. And you have to try and think deeply about what work really means. You have enterprise architect machines who do things and turn things into other things. You get a thing, you turn it into another thing. Right? This is basically what we do. I'm sorry about this. We are little machines that take a thing and turning it into another thing, whilst working within the algorithms of the artificial general intelligence called the company we work in. We take a thing, turn it into another thing. And you can implement this. You can implement things like synchronization, you can implement scheduling, implement queuing, these kinds of things. And you can use tools from game design. This is a behavior tree. It's a finite state machine in a graph form. And you can write these in various languages. I'm writing in C# at the moment. Because I like C#. What can I say? And then you can do things like this. And this is an example of a simulation, a very simple simulation comparing Agile and Waterfall. Well, I mean a single piece flow, a single piece of work flowing through a system, flowing through a value stream versus 100% batches flowing through a value stream. 100% batch, everything has to be analyzed, everything has to be developed, everything has to be tested before moving on. And what you get every time you run it, and it will be no surprise to you after this talk, I'm sure, is if you use single piece flow, the cumulative value of reducing batch size to its smallest amount, the cumulative value that you accrue over the time you run the simulation is orders of magnitude more than using a stage-gated or waterfall process. And you can change the batch sizes. We'll wait for 5 things to be done before moving into. We'll have a sprint for 2 weeks, and we'll take 2 weeks of work on a release train. And every single time, as I'm sure you can imagine why, single piece flow will beat that, will beat release trains. If you pick up a piece of work, do it through to completion, that's more effective in terms of earning us money, saving lives, or whatever we do day to day. And the lead times, well, yeah. The lead times are worse in waterfall, shall we say. Okay, so I'm pretty much out of time, so I'm going to summarize. Artificial general intelligence is already here. We call them companies, and we get paid to execute their algorithms very slowly. We're sitting there picking up stuff, moving it on, picking up stuff, moving it on. There's some principles for you. Go read the book. It's brilliant. I read it about 4 times now. The first time I read it, didn't understand it. The second time I read it, blew my tiny mind just clean off or out through my ears or something. Fantastic. There's a bunch of books you can read about this stuff. See, I've been noodling about this. I think all this stuff, this is sort of stuff that we do that seems to work. And then we've got how it works. And I think there's a set of sort of underlying principles behind a lot of this, which is to do with complexity, which is to do with maths fundamentally. And you can take a look at some of these books, because I think it all flows from information theory, complexity science, and so on. Who can answer that? What would Lego do? If Lego were to try and build a better system of building Lego, what's the one thing Lego could do based on what I've told you? Sorry? Smaller pieces? Yeah, we could just use smaller pieces. Would that be interesting to simulate that? Smaller bags. Whoever said that. Good job. Because they transitioned, right? If you remember years ago, they used to, well, when I was a kid, you just used to, well, even like 10 years ago, you just used to have a ton of Lego in random bags. Now when you buy a Lego set, you have a small bag with just enough to build a couple of pages. So what Lego would do is they'd use small batches, basically. So there you go. Batch size reduction is the key. Thank you very much. I'm done.